Welcome to the Missouri Department of Transportation TIA Guidance PTV Vism software video. This video corresponds with the MoDOT Engineering Policy Guide EPG 905.3.5.2.2. This video is divided into 4 sections. The first section will cover the necessary elements needed to develop a base model to be used in existing year operational analyses and to serve as a template for future year alternatives analyses. The second section will cover adjustments to the base model to better calibrate it to replicate conditions experienced in the field and represented by data collected in the field. It also will cover the basic model validation process after calibrating the model, as well as introduce the modeler to common techniques to fix errors in the modeling process within Vism. The third section highlights the analytic results that can be extracted from model runs and how to use the model to visualize the output data and to create model animation and video files. The final section is dedicated to specific common applications of Vism. This video will review the features and capabilities of PTV Vism Microsimulation software package, explain how Vism is used in the project analysis process, and illustrate the strengths and limitations of Vism. Ultimately, this knowledge will allow the practitioner to determine the appropriate evaluation tool for their project's needs. To learn more about how to use the software, please refer to the accompaniment to Vism in EPG 905.3.2 and to 905.3.5.3.2 of the EPG. Vism is a highly sophisticated traffic analysis software package which has been used for over 20 years throughout the United States and around the world. It is often used as the evaluation tool for industry and academic research projects. Vism is a microsimulation model that generates individual vehicles on a discrete sub-second basis and tracks their interactions to determine measurements of flow, speed, and density of the traffic stream. These models are ideal for analyzing complex and non-traditional urban street networks and freeway systems. Unlike simpler deterministic models, these models can make predictions of density, speed, delay, and queuing for multiple intersections and freeway segments where network interactions are a key feature. These models generally have more refined calibration parameters, flexibility, and scalability than simpler software tools. In addition to the capabilities already mentioned, Vism allows the coding of multimodal transportation features, including pedestrians, bicycles, and transit, and allows the evaluation of their interactions with the vehicle stream. Conversely, the sophistication of these models can require more time and resources than are needed for smaller, isolated, or planning-level analyses. In the broad terms, Vism is best suited for non-traditional, more complex transportation network analyses that are beyond the capability of other modeling software. The first step to using Vism is base model development, where recommended parameter values are specifically defined. Because of the complexity of microsimulation and the amount of time required to complete traffic models, defining a clear model boundary at the outset of every project is vital. Therefore, the initial step in developing a base model in Vism is to develop a scope, outputs, and study area for the modeling effort. EPG 905.3.2 and EPG 905.3.5.3.2.2 provide details to help with this. When a model is first developed, some initial assumptions for global parameters are needed. Many such parameters and MoDOT preferences have been coded in a base file that is available at the initiation of each project. Once adjustments to base data are set, the initial model network can be coded on aerial imagery provided by the software or any other base mapping files, such as CAD, GIS, and other aerials that are imported and correctly scaled. Initial links are drawn on the base imagery and connected at intersections or other roadway junction points, for example, where turn lanes occur, through the use of connector elements, which function like the links themselves. The initial roadway network can have additional basic elements added to the links and connectors, such as desired speed decisions, where a speed limit changes, and reduced speed areas, where horizontal curvature necessitates a temporary reduction in speed, such as for left or right turns at an intersection. The MoDOT Highway Safety and Traffic Division Office or local traffic staff can provide base-level model files upon request. The next logical step in the development of a Vism base model is to add appropriate traffic control measures on interrupted flow facilities. Generally, this includes the coding of stop signs, traffic signals, and rules for priority of movements at any junction where two traffic streams intersect. Stop signs are placed at the precise location of a posted sign or stop bar and will cause vehicles to stop for a specified duration. In addition to the stop sign, the coding of conflict areas or priority rules is needed to control which vehicles have priority and the aggressiveness of the conflicting traffic. Conflict areas are typically easier to code and work for most routine interactions, but priority rules give the analyst more control for more complex situations. It is the analyst's discretion to utilize conflict areas or priority rules for controlling vehicular interaction. For traffic signals, all signal head locations are coded at the stop bar for each lane and movement affected by signal control. The signal head locations are linked to external files set up within the Vism software that control the signal logic, including cycle lengths, splits, and offsets, as well as minimum green times and yellow and all red indications. Several signal control modules are available to input this information, with the RBC controller interface being the most flexible and commonly used. Pavement loop detectors also need to be coded to allow actuated signal control. Existing signal timing plans may be provided when requested. The local MoDOT traffic office should have this information for existing traffic signals. The last step in developing a base year Vism model prior to initially running and testing it is to add vehicles to the network. First, vehicle compositions are coded into lists that reflect the proportional breakout of vehicle classes, such as cars, light trucks, and tractor-trailers. This is applied to all network entry points and is refined for specific locations and time periods of the simulation. Next, the actual traffic flows at all network entry locations are added and quantified to specified durations and for the previously defined vehicle compositions. After traffic is assigned to the network, it must be correctly routed through the network to match field counted or future forecast turning movements. There are two ways to do this. Static routing, which is defined by assigning specific volumes and proportions to origin-destination paths through the network, or dynamic assignment. For networks where path choice is limited, static routing is generally the most direct way to assign traffic flows. If multiple paths exist and there is some level of confidence that traffic would choose routes to optimize time or cost, then the use of dynamic assignment could be considered. MoDOT typically uses 15-minute durations for vehicle inputs and routing if data is available at this level of detail. Finally, multimodal elements can be added to the model if they were included as being important factors during the project scoping process. This includes coding of transit routes, headways, and defined transit loops, pedestrian networks including crosswalks, and bicycle lanes or interaction of bicycles in mixed traffic lanes. Count data for pedestrians and bicycles is also necessary for these features to be accurately accounted for in the simulation. MoDOT suggests the inclusion of multimodal elements in the simulation analysis if they are expected to have an impact on the evaluation of existing or future conditions. Vism models also commonly include evaluation collection elements related to measure of effectiveness, or MOE, output and 3D objectives for visualization purposes. Evaluation elements include the coding of node polygons at intersections in the network, travel time segment start and endpoints, which will collect aggregate travel time and speed data for vehicles passing between two defined segments, the activation of evaluation data collection features for individual links, and ability to collect lane-by-lane data within each link, and the placement of individual data collection points or queue counters, which can be used to collect vehicle count data at a specific location or vehicle queue lengths from a defined location. The inclusion of the 3D objects is not necessary for network evaluations, but can be important for visualization of project impacts. Vism includes a library of stock objects such as trees, buildings, and other features that can be placed within a model. It also includes the ability to include signal poles and mast arms for additional realism. In addition, customizable objects developed with offline graphic software programs can be inserted into the Vism 3D environment if desired. After all base model inputs are completed, the next step is to test the uncalibrated model for coding and logic errors. Prior to running the model, it is good practice to have another analyst with Vism experience review basic elements in the model for accuracy and completeness. A detailed table for this step is located in EPG 905.3.5.6. After the review has been completed, run the model and perform a detailed visual inspection of the animation. The visual helps to identify vehicle routing and input errors, as well as signal operation errors. It also sets the foundation for model calibration and identification of areas where the base model and its default parameters may need adjustment. After the model run is completed, inspect the ERR file that is created at the end of the run to identify model coding errors. The ERR file will alert the modeler to links where vehicles cannot complete their intended route and are being diffused or removed from the network, where and when signal timing errors may be occurring, and which network entry locations are unable to process their intended vehicular demands. For congested networks, it may not be feasible to eliminate all diffusion errors, but review of the file will aid in identifying the critical links where calibration changes will eliminate most issues. There are a wide array of model inputs that can be calibrated from default values to allow model traffic flow results to match observed or collected conditions. These values should be reviewed for reasonableness when making changes from the default values, and they include the following general items. Lane change values apply to connectors between links and the distance at which drivers begin to position themselves to safely assess the connector and subsequent downstream link. The default value of 656 feet or 200 meters is inadequate for most freeway modeling situations and locations of upstream exit signage can be used as an initial reference point to determine a more appropriate lane change distance. The distance can also be adjusted to be applied on a per lane basis, so a 1,500-foot lane change applied to an adjacent travel lane will be extended to 3,000 feet for the next lane further from the connector. Driver behavior model changes can be made to fine-tune traffic flow on freeway and arterial facilities to vary the aggressiveness of individual vehicle interactions and, ultimately, affect the capacity and throughput of vehicles along individual network links and connectors. Driver behavior adjustments and valid ranges of values to change in the calibration process are found in the Vism Calibration Parameters Guidance in EPG 905.3. Default speed distributions can be modified if point or segment speed data is available and would be used in conjunction with setting desired speed decision points to more accurately reflect field observed travel times between points in a Vism network. These speed distribution adjustments should be collected and applied only in areas where free flow conditions exist in the model and not in congested locations. Adjustments to conflict areas and priority rules can have similar effects of aggressive or passive behavior at stop or yield-controlled junctions. Finally, network components, such as link gradient, can be modified to affect acceleration characteristics, particularly of large vehicles. In general, these network element parameter changes, which include the lane change distance adjustments discussed previously, should be adjusted first before attempting more global changes to driver behavior parameters. Prior to fully calibrating a base year model, several other decisions need to be made to ensure three things: that the model results are within allowable statistical variances, that the model is achieving equilibrium prior to calibrating specific peak time periods, and that the model run is long enough to capture congestion effects and properly loads all traffic demand. Prior to peak period evaluation, determine an appropriate seating period to fully load the model with traffic prior to peak period evaluation. MoDOT recommends a minimum of 15 minutes of seating or longer for larger networks where model trips need to be able to fully reach destinations. Another important constraint is model run duration. Model run duration includes the seating period, the peak period under evaluation, and a dissipation period after the peak if needed, to ensure that congested conditions dissipate so all demand can enter the network. If the analyst is satisfied that after running the full model duration, congestion does dissipate in the post-peak period, then the model duration for collection of MOEs can be set to the end of the peak period to avoid unnecessary additional model run time. Finally, determine the number of model runs, choosing consistent random number seeds to produce variations of traffic demand within the model. MoDOT TIA guidance provides details of these processes in the Initial Simulation Runs section and recommends a minimum of 20 model runs. This number can be reduced to a minimum of 10 if the initial sample for a characteristic shows low enough variability to be confident that the model will produce consistent replication of results. Model validation is the process of comparing model outputs to field collected data to verify that the model calibration process is producing reasonable, realistic traffic conditions. There are several criteria that all need to be satisfied to validate a model to real-world travel conditions. First, compare model-reported and field-collected traffic volumes on freeway segments, ramps, intersections, and entry and exit links to ensure traffic volumes have been properly input and routed throughout the model. This also ensures that model throughput in congested areas is occurring to the extent and for the duration as indicated by field data. Secondly, compare travel times between key points in the model and real-world data obtained from field travel time runs or big data sources. Adjustments to default or assumed speed distributions may be necessary to align model travel times to existing field conditions. Next, using visual inspection or review of output data, correlate model and field determine critical locations where queuing is occurring, specifically the onset and duration of congested conditions and the location of bottlenecks. Specific guidance on thresholds is available in the MoDOT TIA documentation, as well as additional resources from FHWA, including the Traffic Analysis Toolbox, Volume 3. Once you've checked for errors, calibrated your settings, and validated the model, you'll receive outputs and be able to create model visualizations. Outputs are generally referred to as measures of effectiveness, MOEs, as they are most often used to compare results between base year and future year models and between alternative designs. These outputs are used in the model calibration and validation process as previously described. The most common MOE outputs from model runs in Vism are travel times and speeds, vehicle delays, vehicle throughputs, link densities, queue lengths, and, potentially, vehicle emissions. Vism will produce separate output files for each level of evaluation, including network, link, individual intersection or node, and corridor. At the link level, evaluation data can be specified for each aggregate link, for each lane within the link, and for specified distances along the link. Additionally, the MOE data can be segregated into separate vehicle types and classes as desired. The process of extracting MOE data produced by model runs in Vism can be done in two ways. The first option is to copy output information from individual output files opened through a text editor program and paste them into a spreadsheet. The second option is to use the list function within the Vism program, as shown here. Data can be produced for individual runs or multiple runs and can include maximum, minimum, mean, and standard deviation output directly from the file run or list. After data is transferred to spreadsheets, it can be further post-processed, aggregated, and visualized using formatted tables and charts. Spreadsheet macros can be readily developed to import Vism external output files and easily update tabular information. An example of a macro-driven spreadsheet is shown here. One common MOE, level of service, is produced internally by Vism in the node evaluation file. If level of service output is desired for other situations involving, for example, freeway segments, then post-processing of appropriately matching sections of the freeway in Vism model to HCM criteria will be necessary. It is important to note that the level of service data derived from Vism results is not directly applicable or necessarily reproducible by a similar analysis using highway capacity software deterministic methods. For that reason, it is common to designate level of service results from micro-simulation programs as LOSS, or Simulation Level of Service. Model visualizations are available both within Vism while a simulation run is occurring and in the post-processing task. Visualizations are commonly used to help understand differences between alternatives or to pinpoint congestion location and duration. This graphic shows a model run where the vehicle color attribute has been modified to show ranges of current vehicle speeds as a color ramp where green would indicate high-speed freeway conditions and yellow, orange, and red indications show continued decreases in individual vehicle speed. Pink vehicles are in the stopped condition, in this case in queues at surface street intersection approaches. The vehicle color attribute can be changed to a wide range of categories, another useful one being routing decisions, in which the modeler checks for unrealistic vehicle movements through a network. Beyond standard formatted tabular results from exported spreadsheet MOE data, spreadsheet alterations of exported speed data or LOS and density data can produce visuals such as the speed contour plot shown here. These types of visuals are useful in determining the location and duration of congestion, whether along a linear corridor for the contour plot or by using color-coded line work of varying thickness to produce heat maps. Vism offers 3 methods to produce animation of the simulation model while it is running for use either within the Vism program or on external media player software. The first method is to develop AVI files while in 3D mode. These files are playable outside the simulation program and require setting up camera locations to record the simulation periods and locations of interest. Use of commonly available video compression software is helpful in managing file size of the AVI files. A second option is to use the storyboard function, shown here, which allows the coupling of keyframes to move from location to location during the simulation run. This method also produces an AVI file. A third option is to produce an ANI animation file during a simulation run. This method allows model simulations to be rerun as a graphical output that can be sped up or reversed to quickly review a model run within the Vism program. Vism ANI files can be exported to other graphic software programs that can render even more detailed 3D simulations. One such example is the 3ds Max software, shown here. This section highlights common project types where Vism is used for evaluation and visualization purposes. One typical category of analysis that is modeled in Vism is surface street networks, specifically extended corridors or urban grid street networks where a high level of vehicular interaction occurs. Vism is capable of accurately modeling coordinated signal systems and adding details for roundabout traffic control and the presence of mid-block minor streets and driveways. For larger networks, Vism can import information from travel demand models to create an initial microsimulation network that can be refined to add the necessary details for increased accuracy. These types of networks can also include on-street parking and additional multimodal details, such as bus stops, pedestrian signalization, and bike lanes. Another common Vism application is the evaluation of freeway facilities, particularly complex and unconventional freeway designs that may not be readily modeled in deterministic software, such as HCS. Like the evaluation of arterial surface street corridors and networks, Vism can model combined system-wide effects of congestion bottlenecks and the upstream shock waves throughout a temporal and spatial context. If correlation with HCS-defined freeway segmentation is desired for a particular project, the Vism freeway network links and connectors can be arranged and divided into the appropriate segment lengths and lane evaluations necessary. To replicate many common HCM-defined basic freeway segments, merge and diverge segments, and weaving areas. It is also possible to modify freeway networks to include manage lane, toll, and HOV facilities, along with truck lane restrictions and work zone evaluations. This is done by coding specific attributes for each lane and defining classes of vehicles, as well as their corresponding input flows and routing to match the situation being modeled. Vism is frequently used in the development, evaluation, and visualization of multimodal networks. The clip shown here illustrates pedestrian and bicycle interactions with traffic flows on an arterial facility designed for an unconventional intersection. The modeling process can include inputs for transit routes and bus stops, along with specific bus dwell times, the potential for skipping stops, and inputs for the expected number of boarding and alighting passengers at each stop. This can also be modeled for light and heavy rail networks. Adjustments to traffic signal or railroad gate control can be added for preemption needs and signal priority for transit. Pedestrian networks can also be developed with the use of sidewalk links and defined crossing areas along with pedestrian signalization. Bicycles can be added in mixed flow situations with vehicles or specific bicycle lanes. Interactions between vehicles, pedestrians, and bicycles can be managed with the use of conflict areas and prioritizing non-motorized flows and movements. As mentioned before, specific evaluations are possible for any mode of transportation coded in the network, allowing evaluation of specific transit vehicles or separation of the vehicle fleet to monitor truck and freight operations. Vism is a useful tool for evaluation of complex transportation projects and designs. Vism has been used for unique situations related to airport curbside operations for departures and arrival roadway systems, alternative designs for freeway and interchange interactions, parking deck operations, and at multimodal transit stations where transit vehicles, pedestrians, and traffic interactions can all be simulated and evaluated. These examples require detailed understanding of the existing or proposed interactions and require additional time and resources to accurately assess each unique situation, but the capabilities of the software offer the opportunity to provide these evaluations and visualizations and have been proven successful in stakeholder understanding and buy-in for past projects. PTV Vism is a powerful micro-simulation tool best employed to handle larger-scale projects that demand a higher level of sophistication to provide accurate evaluations of existing and future transportation network scenarios. As such, some of the advantages Vism offers are a high level of simulation capabilities to handle complex situations, particularly for multimodal projects and evaluations of transportation systems. The details that can be built into Vism models offer a level of realism that may be necessary to handle these scenarios. The detailed level of outputs available from model runs are also useful in the comparative evaluation process. Animation capabilities that allow it to be a useful and necessary tool for public meetings and situations where having only static data and output do not clearly convey the impact of a particular project scenario. Flexibility in the development of models and the level of detail to which inputs and outputs may or may not be necessary to make the critical comparisons needed in evaluating alternatives. Common use across a wide range of public agencies throughout the United States and the world for over 20 years for sophisticated micro-simulation analysis. It is often used by research universities for advanced testing and evaluation of transportation research projects. As for the cons of the software, some of these advantages can also be a detriment in providing time and cost-efficient results for smaller scale or planning level analyses. The time and resources initially needed to code networks can be much larger than using other deterministic or micro-simulation software tools. Couple that with the level of detail and review needed in the error checking and calibration process, and it becomes readily apparent that the choice of software to adequately handle a problem is a critical decision in the project scoping process. Additionally, while Vism produces a wide range of robust output data for use in evaluation in most cases, the data must undergo post-processing in spreadsheets and databases to make useful tabular or graphical comparisons. The level of detail required to accurately develop models in Vism may be more than necessary or be beyond the amount of available data for higher level analyses. For example, without scaled conceptual designs to code network links on, Vism would be cumbersome to develop an analysis for a project where many unknowns may still exist. Deterministic software packages would be more efficient in this case. Likewise, if new signals are being evaluated, the use of Synchro or a similar software tool that can quickly input basic parameters and evaluate different timing options would be a better choice than Vism. There are several resources available to you as you use Vism. As previously mentioned, MoDOT has developed a Vism model reviewers checklist that should be used for internal reviews for initial errors and is also valuable for overall project external reviews of the entire modeling process. Every Vism model submitted to MoDOT will be reviewed by a member of MoDOT staff using MoDOT's Vism Model Reviewers checklist. When using this checklist to review a model, a mark in the check column by the reviewer indicates acceptable items. A mark in the NA column indicates that the item does not apply to the model being reviewed. If an item applies to the model being reviewed but is deemed unacceptable or in need of adjustment, both checkboxes for that item should be left blank, and the reviewer should address this issue with that item in their comments at the end of the checklist. The items in this checklist accompany MoDOT's EPG 905.3.5.3.2. Modelers and reviewers should refer to this section if they need clarification on MoDOT's best practices regarding Vism. The HCM6 contains an abundance of information about using Vism as an analysis tool. For further information, reference the MoDOT Engineering Policy Guide, EPG 905.3.5.3.2. The links shown here navigate to FHWA's Traffic Analysis Toolbox and to the PTV Group Vism resource page, which includes additional tips, techniques, and examples. Time to see what you know. Question 1. Which of the following is not a typically used criteria for micro-simulation model validation? Is it A, vehicle throughput, B, travel times, C, seating period, or D, bottleneck locations and duration? The correct answer is C, seating period. Question 2. True or false? MoDOT mandates the use of priority rules to control vehicle interactions on two vehicle paths that cross, rather than the coding of conflict areas. The correct answer is false. MoDOT allows the model analyst to determine which feature to use when controlling conflicting vehicle paths. Question 3. Some common applications of Vism include A, transit signal priority, B, multimodal evaluations, C, roundabout interchanges, or D, all of the above. The correct answer is D, all of the above. Thank you for watching this video on TIA guidance for Vism. We encourage you to view the other TIA guidance videos. If you have any questions, please reach out to MoDOT Central Office Highway Safety and Traffic.